Hi guys, in today's lesson on mathematics, we're going to keep working on modular arithmetic. In our previous lesson, we looked at the history of modular arithmetic. We discussed great mathematicians like Ramanujan. We talked about the great work by the father of modular arithmetic. We talked about Carl Friedrich Gauss, the great work he did in 1801. So we looked at the history of modular arithmetic, and we also looked at some nice introduction to it. So today we're going to be looking at a couple of things such as this. So in this very lesson, we're going to be starting with basic operations on modular arithmetic. That's the first thing we're going to be looking at today, basic operation. In this lesson, we're just going to focus on this. And next, we're going to be looking at the equations, the various equations under modular arithmetic. And the last thing we're going to be looking at, we'll be looking at other applications. We're looking at other applications on the modular arithmetic. So in today's lesson, you're going to be looking at basic operations. There are four major basic operations under modular arithmetic. We have the addition operation, we have the subtraction, I have to classify these two together, and then we have the multiplication and the division operation. So we have addition and subtraction, and after that we have multiplication and division. These are the basic operations under modular arithmetic. So once we're done with this, the next thing we're going to be looking at, we're going to be looking at various equations, and after that we're going to be looking at other forms of application, the various ways modular arithmetic is being applied. We discussed some of the applications in our previous lesson, but we're going to be looking at different calculations on them. So today we're going to be starting with addition and subtraction. Addition and subtraction operation under modular arithmetic. So now quickly, let's assume that we have something like this. Let's assume that we have 3 plus, let's say we have 3 plus 4 in modulo 5. Now we're talking about modulo 5, don't forget that the highest number we know under modulo 5 should not be up to the modulo 5. Once a number gets to the modulo 5, just like base 5 under number base, once a number gets to modulo 5, that number is being simplified. And when that number is being simplified, the number turns to 0. We said in our previous lesson that modular arithmetic is more or less like clock mathematics. You can call it clock mathematics because when you look at the clock, when you look at the calendar, when you look at different stuffs, obey modular arithmetic. This modular arithmetic is applicable when it comes to various, activities, various things in our environment. So we're talking about 3 plus 4 modulo 7, modulo 5, I beg your pardon. This is very simple. We can just solve this already. You can say 3 plus 7. 3 plus 7 is plus 7. 3 plus 5, I beg your pardon, is plus 7. So how do we write plus 7 in modulo 5? If you have not seen the previous lesson where we talked about the history and the introduction into this, I'd love to go and see it. So plus 7, if plus 7 will be written in modulo 5, how are we going to do that? We're going to do this by dividing plus 7 with 5. 5 in plus 7 is 1, remainder 2. So don't forget that plus 7 is up to 5 and even more than 5. So if you're talking about modulo 5, the highest number should be 4. Just like number base, just like base 5. So plus 7 being reduced, you're going to get 1 remainder 2. So 3 plus 7 in modulo 5 is equivalent to 2 modulo 5. This is the result. So this how to solve this is very, very simple and direct. We could also do something. We could create a kind of operation table that shows addition of various numbers that fall between the modulo 5. Don't forget that 3 and 4 falls where among the set of numbers in modulo 5. So you can quickly create an addition operation table. You can create something like this. Since you're talking about modulo 5, you have 0, you have 1, you have 2, you have 3, and we have 4, which should be the maximum number. So that's 0 to 4. So you're going to create the same set of numbers on this very axis, on this very y-axis. So right here we have 0 also, we have 1, we have 2, we have 3, and the very last digit we have 4. So we are talking about this operation table. We are talking about addition of numbers. Don't forget 3 and 4 well placed among the set of digits that make up modulo 5. So let's quickly work on them. 0 plus 0. Now don't forget this is addition of numbers. Now whenever we're talking about addition of numbers, when it comes to addition of numbers, just like a plus b is equals to b plus a. So what does this mean? For addition of numbers or quantities, addition and multiplication especially, they are commutative. So when we say something is commutative, it means we could swap their position. 1 plus 2 is same thing as 2 plus 1. We're going to get the same result. 1 plus 2 is 3, 2 plus 1 also is 3, unlike subtraction of numbers. A minus b is not equals to b minus a. So when it comes to subtraction and division are not commutative, but addition and multiplication, they are commutative. So this is non-commutative. So this is not commutative. So what does that mean? It means you can add like this, you can go like this, or we could go like this. So quickly, let's solve. So 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 2 is 2. 0 plus 3 is 3. 0 plus 4 is 4. Now, don't forget, all these are well written down, easily written down, because none of them is up to the modulo 5 we are talking about. So just drop them. So 1 plus 0 is 1. 1 plus 1 is 2. 2 is not the modulo 5. Just drop them. If you try to use 5 to reduce 2, 5 and 2 is 0, remember 2. So you see, we're still going to get the same thing. 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 4 is 5. That's the first result that is up to the modulo. So 5 and 5 is 1. 1 remainder 0. So we're going to write our 0 here. 2 plus 0 is 2. 2 plus 1 is 3. 2 plus 2 is 4. 2 plus 3 is 5. 5 and 5 is 1 remainder 0. We're going to write remainder 0 down. 2 plus 4 is 6. 5 and 6 is 1 remainder 1. So we're going to write down 1. So 3 plus 0 is 3. 3 plus 1 is 4. 3 plus 2 is 5. We're going to write 0. 3 plus 3 is 6. We're going to write down 1. 3 plus 4 is 7. Write out 2. 5 and 7 is 1 remainder 2. So for the very last set, 4 plus 0 is 4. 4 plus 1 is 5. We break it down. We have our 0. 4 plus 2 is 6. 5 and 6 is 1 remainder 1. Write down 1. 4 plus 3 is 7. 5 and 7 is 1 remainder 2. We have our 2. 4 plus 4 is 8. 5 and 8 is 1 remainder 3. We have our 3. So this table is well set out. This is addition table under modulo 5. So let's quickly see if this table is going to answer this very question. 3 plus 4 in modulo 5, what's it going to be? 3 plus 4. 3 plus 4. Coordination. So 3 plus 4, what I'm going to get? This 3, this is 4. Our answer is 2. 2 modulo 5. As simple as that. You can also go this way. 4 plus 3 is the same thing. Or 3 plus 4. 3 plus 4. 3 plus 4 is also 2. Even 4 plus 3, when you look at it, 4 plus 3 is also 2. So whichever way you go about it, you can see you're going to get the same result. So that is that for addition operation under modular arithmetic. So quickly, let's look at the subtraction operation. So when we have, and we say this is also 1b, this 1a, this is 1b. So we have 3 minus 4 in modulo 5. How do we solve 3 minus 4 in modulo 5? How do we solve this? You can solve it the simple way or the direct way. So when we look at 3 minus 4, we give us minus 1. So we're going to combine minus 1, we write it in modulo 5. So how do we do that? So that would be minus 1 over 5. So minus 1 divided by 5, how do we do that? We can create our table, a simple 5 times table. But this time around, you're talking about negative result. 5 times 0 is 0. 5 times minus 1 is minus 5. So as you can see, we are looking for minus 1, and we have minus 5 here. Don't forget that when it comes to division of numbers, if you cannot get the exact number you're looking for, then you have to go with a result or a digit that is nearest to it. 0 is bigger than minus 1, so we're going to go with minus 5. Minus 5 is very close to minus 1. It's smaller than minus 1. So it's not minus 1 actually, but it's very close to it. So for those that have seen the previous lesson, they understand what I'm doing here 100%. This minus 5. So 5 and minus 1, they give us, that's minus 5. We're going to pick this. So what's our answer? Our answer is minus 1 remainder. What are we looking for? Minus 1. What did we get? Minus 5. So that will be minus 1 minus minus 5. Minus 1 plus 5. That will give us 4. So minus 1 remainder 4. So when we convert minus 1 to modulo 5, we're going to get 4 modulo 5. That's the result. As simple as that. That's the result. So don't forget, We also said something in our previous lesson that whenever we are asked to convert negative result or negative numbers to any given modulo, we can convert the positive result. As you can assume, since this is -1, you can convert 1 to modulo 5. Then when we convert 1 to modulo 5, there's something we're going to do. We just take off that very modulo, that very remainder from the modulo itself to get the result of the negative result. So let's quickly do that. So this is what we're going to do. -1 to be written in modulo 5. You can assume that -1 is 1 to be written in modulo 5. Just assume that we take off the minus sign. We just work on the positive. So if you're going to write 1 in modulo 5, what's it going to be? 5 in 1 is 0 in modulo 1. So 1 in modulo 5 is T1 modulo 5. So after getting this, -1 then is going to be what? We take this 1 away from 5. 5 minus 1 will give us what? 4. 4 modulo 5. We worked on this in our previous lesson. So these are to work on negative figures under modulo arithmetic. So it's very simple. Also, we can create a subtraction operation table, just like the way we created the addition operation table. You can simply do that. When we create the negative, the subtraction operation table, what we're going to do is that, okay, let's quickly look at that. So here is the subtraction operation table under modular arithmetic. So this is what we're going to do, just like the way we approached the addition, table. So here we have 0, 1, 2, 3, 4. Right here we have 0 also. This 1, 2, this 3, and lastly we have 4 on the very end. So this is what we have. Now don't forget something. This is not like the addition operation table. For addition operation table, whatever we do here is commutative for addition operation table. But this is not the same for subtraction. So you're just going to keep at it, 0 minus 0, 0, like that. So 0 minus 0 is 0, 0 minus 1 is -1. Now, one thing is this, when you compare this very table with the addition operation table, what happens is that we write the very first result for that addition operation table, then we write the other result from the back, like that. So as I write it, you can compare it with the other table to see the similarity that we have. So yeah, 0 minus 0 is 0, 0 minus 1, and 0 minus 1 is -1. 1 in modulo 5, that will give us 1 modulo 5, so 5 minus 1 is 4. 0 minus 2, 0 minus 2 is -2, 5 and 2, ordinary 2 is 0, modulo, next to modulo 5, 5 minus 2 is 3, 0 minus 3, you know what it is, -3, 5 and 3, that's 3 modulo 5, also that is 2, 0 minus 4, that's 1 also. So 1 minus 0 is positive 1, so that is just 1, 1 minus 1 is 0, 1 minus 2 is -1, and combine -1 to modulo 5, you're going to end up having, that's 4 modulo 5. So 1 minus 3 is -2, convert ordinary 2 to modulo 5, that gives us just 2 modulo 5, 5 minus 2 is 3, 1 minus 4 is -3, ordinary 3 to modulo 5 is 3 modulo 5, that's 2, 2 minus 0 is 2, 2 minus 1 is 1, all this in modulo 5, don't forget 2 minus 2 is 0, 2 minus 3 is -1. -1, let's assume that it's ordinary 1, 1 in modulo 5 is just 1 modulo 5. So if it is minus, that will be 4. So 2 minus 4 is -2. Now let's assume that it's 2 in modulo 5, that is just 2 modulo 5. Come back to minus, that's 3. So 3 minus 0 is just 3. 3 minus 1 is 2. 3 minus 2 is 1. 3 minus 3 is 0. So 3 minus 4 will give us -1. So -1, let's assume +1 to modulo 5 is 1 modulo 5, that is 4. And you come back to minus. 4 minus 0 is 4. 4 minus 1 is 3. 4 minus 2 is 2. 4 minus 3 is 1. 4 minus 4 is 0. As simple as that. So when you compare this with the addition table, we found out that they share something. What they share in common? These figures remain the same. But all these ones were written from the back. Unlike the addition, when you look at the addition table, it is 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. So you see, the 0 is constant. We'll just change the table to compare. So quickly, let's up 3 minus 4 will give us what? 3 minus 4. 3 minus 4. 3 minus 4 will give us 4. As you can see, it's 100% correct. 4 modulo 5. As simple as ABC. So you could use your operation table or you could just use the zero method. Now, operation table is very applicable provided the numbers given to you are part of the figures that make up the modulo. For example, if you have 17 minus 10, there's no way we can really create an operation table that will house this because the numbers that will make up the modulo we're talking about should not be up to the modulo or even more than it. So you're going to be seeing some questions to get us tested. Okay, guys, we have a couple of questions on the board to get us tested on how much we've gotten from today's lesson. So we have four major questions on the board. We have number one, that's 1A, 5 plus 7 to be written in modulo 8. 5 minus 7 to be written in modulo B, that's 1B. Then 2A, 11 plus 24 to be written in modulo 5. And then 2B, 11 minus 24 to be written also in modulo 5. I'm very sure that we have what it takes to solve all those very questions on the board. So we've come to the end of this very lesson. In our next lesson, we're going to be looking at multiplication and division operation under modular arithmetic. So if you gain one or two things from this very lesson, I would love you to give me a follow on Facebook at Revelation Hub and subscribe to the very channel at Edge Mosaic and share this lesson also with others. See you in the next lesson. Thanks, bye for now.